The magic of snow, travelled from afar. Snowfall, and the marvelous transformation of the landscape, is becoming an increasingly rare event. Over the past years, snow has been falling later in the season and lies for a shorter period of time. Winters, as we know them, are shrinking. Is snow itself threatened with extinction? And if it is, what will happen to all the life which depends on snow for its survival?
When it's cloudy and really cold, that's when it can snow. Clouds carry inside them huge quantities of humidity, which can condense and fall either as snow if it's cold enough, or as rain depending on the temperature. Those cloud formations are called atmospheric lows. So in the Alps, it's these low-pressure systems that bring us snow. They arrive here in different ways. One way is when they travel across from the west over the Atlantic Ocean. Then, if it's cold enough, we can have large snowfalls.
On our planet, we have weather systems that move from a west to an east. It is done so by what we call a jet stream. So if we concentrate on the northern hemisphere, we have a jet stream that is located roughly around 35,000 feet up. And it has these waves in it. And where these waves occur, they move air masses, warm ones north, cold ones south.
The weather systems observed by climatologist Mark Wysocki are the low-pressure systems that bring with them strong winds and rainfall. These immense cloud layers move from the Sea of Japan across the North Pacific before they travel through the United States. On their way, carried by the jet stream's powerful winds, the winter lows interact with America's Great Lakes, picking up moisture and heat before heading out over the Atlantic towards Europe. The Earth's orbit around the Sun drives seasonal change. As the South Pole moves closer to the Sun and the North Pole moves away from it, winter arrives in the Northern Hemisphere. But winter has yet to come to France. The country's southern Alps are basking in the Indian summer sunshine. With no snow on the pastures, the sheep continue to graze. Livestock here moves seasonally between fields in the mountains and valleys, an ancient farming practice specific to these regions between the Alps and the Mediterranean. Sheep spend the summer season in the Alpine pastures. They'll return to the valleys between September and November before snow begins to cover the mountains again. While the sheep are grazing, preparations for winter at Les Ors ski resort are already well underway by the end of September. Snow guns are set in position to secure snow cover on the ski slopes. The effects of global warming are changing the seasons in the Alps. Spring and summer are hotter and drier, while winters are shorter with less snow cover. The consequences of these changes can already be seen. The late onset of snow gives the black grouse population a last opportunity to gather before they disperse for winter. These little clearings are where the male birds perform their courtship dances every year. The birds will return to the edge of the forest, where they find their winter sustenance, larch buds and pine needles. The black grouse is a threatened species in the Alps. Snow is an important winter feature for them because it's by digging igloos into powder snow that they're able to survive the coldest months. Snow cover also helps to insulate burrows where marmots hibernate. By the end of the summer, these little mammals, part of the squirrel family, must have accumulated enough fat to survive their big sleep between October and April. There's only one breeding pair in a marmot family. The other young adults, although sexually mature, help the breeding pair to raise their young, especially during hibernation. For survival, they need to snuggle up with the pups. Longer summers, milder winters, seems to be ideal conditions for marmots. But animal survival rates and climate change are a much more complicated picture than we might expect. The snow hare is still wearing its summer camouflage suit. Come winter, its coat will turn from grey-brown to snow-white in just 2 weeks. The shortening of daylight hours as winter approaches causes the hare to molt, whether there's snow or not. Global warming is not good news for this hare. Without snow for camouflage, the hare's white coat makes it an all too visible target. Increasingly mild temperatures at low altitude also reduce the hare's natural habitat, confining it to the highest mountains. The snow hare has already disappeared from the Vosges and Pyrenean mountain ranges. In France, the Alps are its last refuge. Icon of the Alps, it may seem surprising to discover that the ibex came close to extinction in 19th century Europe, a victim of hunting. But it's thanks to the ibex that France's first national park was created in 1963 in La Vanoise Valley. Today, 8,000 ibex roam the French mountains. The ibex is an outstanding rock climber, more agile than a chamois, in spite of being much heavier. A male ibex can weigh up to 90 kilos, and few animals can equal its performance on the rock faces. These animals protect themselves from freezing temperatures with a 4-layered coat, 2 long layers and 2 short and dense ones. The ibex have in common with the mountain hare, the marmot, and the black grouse specific adaptations necessary for life in the snow at high altitude. It is these adaptations which shape life forms in the mountains and lend them their beauty. The same is true for alpine plants.
Alpine plants are a miracle of engineering, adapted to dealing with really difficult conditions, hugely contrasting temperatures, snow cover, absence of soil, frost and thaw cycles. They're really worth paying attention to. Okay, Lose summit, Androzes helvetica. Okay, I'm on my way again. In the mountains, the period during which plants can photosynthesize, grow, develop, and actually live their lives is, in fact, relatively short.
This means that to survive, alpine plants need to take advantage of the snowpack, which covers them for a large part of the year.
The rhododendron, a plant many people are familiar with, doesn't shed its leaves in winter, so this means that for 12 months of the year, it can photosynthesize, capture light energy to produce its own matter. But when a plant photosynthesizes, it makes gas exchanges. It captures carbon dioxide and releases water. The problem with this in winter in the mountains is that water freezes, so if the rhododendron wants to survive, it has to stop photosynthesizing at some point. One way to do this is to be in the dark. Darkness prevents plants photosynthesizing. So the rhododendron needs a thick blanket of snow over it. 20 centimeters of snow is not bad, 30 centimeters is better. Mechanically speaking, the plant is totally adapted for this. Its branches are almost unbreakable, so the rhododendron can cope with big accumulations of snow lying on top of it. In spring, when snow melts, it becomes denser and heavier, but the rhododendron's wiry branches still don't break. As the snow melts, the snow cover shrinks. When it's less than 20 centimeters deep, the rhododendron begins its gas exchange again under the snow. The plant is ready, it loses no time. In spring, it's already active under the snow. It's a survival strategy which maximizes light and the growth period for the rhododendron. It's risky, of course, but life is not without risk.
On the other side of the Atlantic, the moisture-laden low-pressure system is advancing over North America. The appropriately named Great Lakes region of North America is crisscrossed by a network of rivers and lakes through which 50 billion tons of water circulates daily. Each second, more than 3,000 tons of water pour over Niagara Falls. These interconnected waterways make up the largest freshwater system in the world. Their formation dates back to the end of the last ice age 10,000 years ago. The retreat of the glaciers northwards carved out deep expanses of water that rarely freeze entirely, despite temperatures 20 degrees below. Water has a high heat capacity, so it takes time for it to heat up. But once it does, it holds its warm energy for longer than air does. These specific physical properties create spectacular weather events across the Great Lakes region. When the low-pressure system traveling from the west reaches the lakes, The meeting of cold air and warm water causes the formation of very large snow-laden clouds. It's a special type of snow, lake effect snow. A group of meteorologists from the University of Oswego is studying this phenomenon on Lake Ontario.
I'll take it from you. There you go. Good.
Gotta catch the wind, so be ready.
Hold on to it tight. We'll do a countdown. Let's go to the corner over there. I might lose my grip, as long as you got it.
I got it.
Got it? Ready, Carl? Yep. I'm letting go.
So this is a really neat sounding showing how deep the boundary layer is here. It's going up to 2 to 3 kilometers, allowing the cloud to grow pretty deep, which is allowing the snow growth region to be very large and giving us very heavy snow out over the lake. All right, the reason why I brought you guys up here is because we have an intense lake effect snowband going on over Lake Ontario. It's all the way to the Tug Hill Plateau. The key ingredient why we get lake effect snow is because we have cold, moist air going over a relatively warm body of water, a large body of water. You know, the longer that cold, moist air goes over Lake Ontario, the more moisture and heat it picks up, the deeper the clouds get, the heavier the snow. So you want cold air going over the lake, but also a lot of background moisture. Now that you know a lot about lake effect snow, the ingredients that make up lake effect snow, I'm going to have you test your knowledge by forecasting for snow tonight. So what you're going to do to forecast is I want you to tell me the probability between 0 and 100% that you think a station in New York State will get at least 1 inch of snow tonight between 7 p.m. and 7 a.m.
Do have an ideal wind component showing some lake effect over in, is that Rochester, I think. Yeah, that's light snow.
What are the sky conditions in central New York?
It's generally overcast. It's actually currently light snow in Rochester. There's a 15 knots northwesterly wind component. That's hard to judge right there. I'm thinking, honestly, more southwest of Syracuse, maybe like near the Hannibal area.
I'm thinking closer to Lakeshore, up towards maybe like Oswego and stuff.
Okay.
There are only 2 places in the world where this weather phenomenon can be observed. Here over the North American Great Lakes, and on the other side of the world over the Sea of Japan. But is this very special type of snow as threatened with disappearance as snowfall in the Alps? The answer is, we don't really know. Water temperature in the lakes will increase over time, favoring lake effect snowstorms in the short term. But in the long term, as global air temperatures rise, there may be less evaporation from the water sources, leading to a decrease in snowfall. Imagine the disappearance of snow in the Northern Hemisphere, the loss of such an important part of our cultural heritage. Carried by the jet stream, the winter low has reached New Hampshire east of the Great Lakes. Snow is critical for these maple, ash, and beech trees because it contributes to the balance of the forest ecosystem. A team of scientists at the Hubbard Brook Experimental Forest is studying the consequences of reduced snowfall on tree growth.
So like other forests around the globe, temperatures are warming here in New England. However, winters are warming faster than other months of the year. So we know that over the last several decades, air temperatures in winter have been increasing about 4 or 5 degrees Celsius. There's less snow compared to the past. So for example, when it snows, it's more likely to melt. And often in winter, we now get rain on snow events, which was unheard of in decades past.
Biologist Pamela Templer has set up a field experiment to measure the future impact of global warming on the development of trees like maple and American beeches.
Wintertime, we remove snow by shoveling to induce soil freezing, and then we kick the cables on to thaw the soils, basically to mimic a future where we get more freeze-thaw cycles in wintertime. So we measure tree growth a number of ways. First, we have what are known as dendrometer bands that we have on each of the individual trees within each of our experimental plots. And basically, they have a spring on them. So as the tree grows this way, like the trunk gets wider, the bands get, stretched out, and we measure how much the bands grow over time. 2.
Back at Boston University, Pamela and her team compare these results with other measurements they make in the field. They collect fallen leaves from deciduous trees. The more the trees grow, the more numerous the leaves are. So the number and weight of the leaves are key indicators of tree growth.
Tree rings are another way that we could measure above ground growth rates of trees. So we take what are known as tree cores from the sides of trees. You could just imagine a core going into the trunk of the tree. We pull it out. We look at that under a microscope, and we can measure both the number of tree rings to get the age of the tree, as well as the space between the tree rings to calculate growth rates of the trees. And so using the microscope, we can get really detailed measurements, and then we can convert those growth rates to how much carbon the trees sequestered in their biomass.
The air we breathe depends on the health of forests. Using photosynthesis, trees absorb carbon dioxide from the atmosphere and produce oxygen, which is vital for life. We thought that forest productivity would increase with warmer temperatures and shorter winters, but Pamela's research conclusions are bleak. Without snow, these northern forests' growth patterns are compromised.
As soils freeze, the water in between the soil particles freeze and expand, just like an ice cube in your cup of water. And as that happens, it physically damages the tree roots that are in the ground. What we're finding is that with a smaller snowpack and greater soil freezing, that the trees actually get damaged by that. And as a result, they don't take up as much carbon. And so that's a really important result if we're considering forests as a carbon sink for the globe. With climate change, I don't think we're going to lose forests entirely, at least not in the near future. However, we're likely to see a change in the tree species composition. So as northern species that rely on really cold winter climates don't have the conditions that they're adapted to, it's possible we won't see as many of them in the future, like sugar maple trees, but we're likely to see other species like red maple and red oaks come up and replace them.
Does less snow mean the disappearance of maple trees and maple syrup? In the Alps, the same threat hovers over the Alpine plants Cédric Danton is so fond of. Meteorological variations can disturb the fragile life balance of these plants, which is often specific to location and sunlight.
In the mountains, the way the slopes are facing is really important. We call the northern slopes the Ubak and the southern slopes the Adrets. The Alpine snowbells don't really have particular preferences in terms of exposure. They'll grow on the south slopes and on the northern ones too. As long as there's snow, they'll grow there. Like the rhododendron, these plants actually start photosynthesizing under the snow. You can see the flowers in late spring. Snowbells pierce the snow, then open their flowers. It's a truly magnificent sight. Snowbells also have a dark stem. It's black in color. Like everything that's dark, the stem accumulates visible light energy and transforms it into invisible light energy, infrared. Infrared is basically heat, so the dark stem helps to accelerate the melting of snow around the snowbell as it grows up through the snow. These are fascinating plants.
But without a blanket of snow to cover them and keep them warm, many mountain plants will have to find other survival strategies. Some are better prepared than others.
When we talk about climate change, what we forget is that some living things actually benefit from it. In the mountains, there has been an increase in the population numbers of certain species. For example, the dwarf juniper, which seems to be really very happy with this warming climate. This plant likes hot and dry conditions and isn't damaged by frost. In fact, it's not really afraid of anything. As you can see, there are more and more of these plants present on the mountainside. If you look closely, mountains are made of many small facets, what we call topography. There are lots of hollow bumps, small north areas, small south areas. This very varied topography means that species can leap back a century in terms of climate over just a few meters. If they migrate from, say, a southern face to a northern face, the north face might have temperatures and rainfall measurements close to those that you might have found 20 meters away on the same slope 100 years earlier. These kinds of migrations, let's say small-scale migrations, can act as refuges. We can call them topographical refuges, and they can be extremely effective.
Migration and the dwarf juniper are proof of plants' incredible capacity for adaptation. But are there limits?
At what point will the benefits level out and lead to a chain of disasters? Once certain plants or certain environments can no longer deal with the temperature changes, with water shortages, there can be a snowball, and that's what we call a threshold effect. From a given moment, but of course we don't know what that will be, the alpine plant ecosystems will no longer be able to deal with such rapid change.
Come in, Tommy.
Affirmative.
I have some bad news. I've just finished my inspection.
And found the stab in the closed position broken. The only way to fix it is going to be to drain the whole system.
Copy that.
I stopped the snow guns uphill.
Roger.
I'm going to run the compressor while you open the top.
At Les Ors ski resort, they're still waiting for real snow to arrive. Leaving the eastern shores of the United States, the low-pressure system is carried out across the Atlantic. 4,000 kilometers from its starting point, it hits Iceland. The island of Iceland sits right in the path of these winter storm systems. But for how much longer? Climatologists report that the jet stream, which plays such a big role in European weather patterns, has been disturbed by global warming, reducing the number of low-pressure systems carried to Iceland, then to France. The storm system follows its course over Europe. The season's first serious snowfall finally arrives in the Alps, and in sufficient quantities to last through the winter. What makes snow so precious? At first glance, it's hard to tell. The thermal insulation properties of snow depend on the structure of its flakes, and that structure changes according to air and ground conditions.
I'm going to dig out a well, so we can see the snow layers really clearly. We're going to have a look at the different types of snow you can find in the snowpack here. They're caused by all sorts of different weather conditions, which I'll describe. On the surface, you have something quite soft, quite fragile. It's not at all dense, so the snowpack here isn't hard. If I put my finger in it, it sinks on its own. So this is cold, fresh snow, which has never experienced liquid water. It's never melted. It has a very fine structure, which makes it look very white. If we take a closer look at its structure with a magnifying glass, which blows it up 8 times, you can see little bits of stars, and there are lots of different shapes in the structure, and it's very, very fine. Then here you can see we have a deeper layer which is dirty. It's full of debris. That's due to a windstorm that happened some time ago, during which a lot of plant matter from the trees came to settle on the snowpack.
It's the air trapped in the snowflakes in the upper layer that lends the snowpack its insulating qualities. But further down, the snow's texture changes.
When I look closely at some of these fragments, we can see that the structure of the snow is much coarser here than it is at the top. The snow is hard because it's been through several cycles of freezing and thawing. It's rained, the snow melted, then it refroze. So the snowflakes have been welded together and become big sorts of clumps. They are literally stuck together, so the snow is very hard and it looks grey. This is because those clumps are bigger in size and able to absorb much more light than the snow in the upper layers, which is much whiter. So now I'm going to have a closer look at some of those bigger clusters. In our jargon, we call them grains.
Snow owes its white colour to a multitude of ice crystals. Like many small mirrors, they reflect light. The bigger grains lose their reflective power. White, grey, blue. Snow changes colour when it changes structure. Near Grenoble, the Centre for Snow Studies holds a series of data sets which are unique in the world. 60 years of uninterrupted measurements of air temperature and snow cover at an altitude of 1,325 meters. This long-term climate change study allows researchers today to formulate hypotheses for the future.
You can see on the graph what has happened over the past 60 years. Here in blue, it shows the change in the average snow depth since 1960 until today. First of all, I think we can see that the blue bar varies enormously from one winter to the next. There have always been, and still are, snowy winters, as well as winters with very little snow. On the other hand, if we look at the averages, we see a big difference in snow cover, with an average around 1 meter over the period 1960 to 1990, but which is now down to 60 centimeters. So that means we've lost 40% of average snow cover here at this site, which is huge. A meter is here, and 60 centimeters is here. So we've lost all that snow. It's a spectacular loss. In terms of, for example, water resources or for the operation of a ski station, it's very, very impactful. This part is the change in air temperature during the winter here, over the past 60 years. When it's red, the temperature is above average, and when it's blue, it's below average. So we can see an increase in the frequency of red years, so warmer than average years, over the past 30 years. Also, if we look at the global warming index, we can see an increase of more than 1 degree over 30 years. So what's going to happen in the future really depends on how hot the air temperature is going to get. Air temperature will stabilize the day we'll reach carbon neutrality, which is the day we'll emit as much greenhouse gas as the Earth is capable of absorbing. Until that day, temperatures will continue to rise, so this is dependent on our actions today. Until we are carbon neutral, snow cover will continue to decrease. In pessimistic scenarios, we are able to model that at a horizon of 2100, at a site like this one, there will be almost no more snow. There may be winters where there will still be some snow, but the frequency of snowless winters will increase dramatically.
At the end of the 19th century, there were 1,000 inhabitants in Les Orres, but by the early 1960s, there were only 235 left. The snow plan was put into place by the French government in the mid-1960s as an attempt to slow the exodus of human populations from mountain territories to the cities. Work began in 1964 to develop the ski resort at Les Orres, then in 1970 with the architect Jean-Michel Legrand. Today, the resort is classified. The architecture of the buildings was designed to echo the surroundings. The facades, which are white, symbolize snow. The upper part, made from larch, symbolizes the forest. So, the buildings are harmonious. They melt into the environment. The jobs provided by ski resorts have made it possible to support families living here and elsewhere in the mountain villages. Here we have cattle and sheep farmers who are also piste groomers, ski instructors, and can sell their farm produce to tourists. That's why we have 560 inhabitants in the district today, compared with the 230 at the start of the 1960s.
France has one of the largest ski domains in the world, with 350 winter sport resorts linked to 400 mountain towns. But increasingly, mid-mountain resorts, situated between 1,000 and 2,000 meters above sea level, are facing unreliable snowfall. 3 resorts have closed permanently every year on average for the past few years. At its peak, the Col d'Arzelier ski resort in Isère, which culminates at 1,150 meters, had 9 slopes and 6 ski lifts. But in December 2018, after 51 years of service, a shortage of snow sounded the death knell for the resort. The station's closure represented a significant loss for the local community's budget. It also raised the thorny and unresolved issue of public financing for an increasingly unviable economic model. Years after closure, the disused buildings and equipment sit on the slopes. There are still no plans for dismantling the resort. Over 100 ghost stations, like this one, are scattered through the French mountains. In less than 60 years, the government plan to bring wealth to mountain communities has been brought to a standstill. With a domain that reaches from 1,600 to 2,007 meters above sea level, the resort at Les Orres isn't threatened with closure. But the station's operators are looking to find a balance between economic factors and environmental imperatives. Managing a ski resort in the context of a warming planet could be considered paradoxical. But for the mayor of Les Orres, the way forward lies in a transition to green energy.
A ski resort is a business, and we manage it as one. But we're also working to put in place new tools to allow us to make a transition. By adjusting the speed of the ski lifts, for example, we've reduced energy consumption by 20%. We're working right now on setting up renewable energy production, particularly by developing hydro in the mountain water torrents. We're also trying to encourage tourists to come here by train and then take an electric shuttle up to the resort, which would mean we could reduce related greenhouse gas emissions by 95%. We want to lower energy consumption, particularly in buildings via insulation, and we've already installed public lighting control systems that allow us to dim lights, but also to switch them off completely after 10:30 p.m.
Alpine skiing became a popular sport less than 100 years ago. But it's possible that it will vanish within our lifetimes. Winter sports stations are trying to remodel themselves while dealing with the legacy of their massive development in the 1970s and their uncertain future. Snow has settled now in the northern Alps. But the snowpack isn't uniform. Between snowfalls, temperature swings alter its state, which can cause serious problems for mountain inhabitants.
On les voit pas, mais ils sont là.
You can't see them, but they're here. And we know they're here, because you see the tracks in the snow, a leftover meal, some scat. With a little practice, you can tell who's been here. There's something a bit magical about tracking them in the snow. About half a metre of snow has fallen, so it'll be difficult for them. They can't get to the grass, they'll have to scrape through the snow. They spend a lot of time during the day searching for food, and when they find it, eating. In summer, the grass is much richer, they spend less time feeding, and they've more time to rest. So snowy winters are difficult for them. The ibex's strategy in snow is to stay in very steep areas. We know that they're very good climbers, so when there's a lot of snow, if they stand in steep places on the cliffs, the snow doesn't stick so much to the mountain face. The steeper the faces, the more snow slides off, and the ibex has better access to the grass. We don't have winters anymore with continuous cold temperatures and permanent snow cover. Temperatures can go from -20 one day and then the next day be positive again. When temperatures warm, the snow melts and sometimes it even rains. When it gets cold again, the water freezes, so the grass is no longer accessible. The last time that happened, the ibex moved into the pine forests. They were eating the fallen pine needles. It was all they had left, and several of them died of starvation. It's better for the animals to have a regular season rather than these ups and downs we've had with big temperature variations.
When snow falls, the snow hare is finally in its element. Its camouflage melting into the white of the landscape. But a lack of snow is not the only risk this hare is running these days.
I study snow hare demography, which means I tried to find out how many hares live in a certain study area and how these numbers might change over time.
Following in the footsteps of an almost invisible animal, Michel Busch has discovered that at an altitude of 2,000 meters, the snow hare has to share its territory with a newcomer to the mountains.
There's competition with the brown hare. It's a competition for space and habitat, because in the context of global warming, we are seeing more brown hares at higher altitudes. There's also genetic competition, since the two species hybridize, and if the hybridization and crossbreeding happen a lot, we could have replacement of the snow hare's genes with those of the European hare. This process is called introgression.
But the war isn't won yet, because the brown hare's anatomy is not as well adapted to the requirements of the high mountains as the snow hares.
The height and depth of snow cover are going to be a limiting factor for the brown hare. It will be more restricted in its movement at altitude, because it doesn't have those big fluffy feet, which allow the snow hare to run through powder snow. I think it's also more difficult for the brown hare to feed at altitude, because it can't feed on woody stem plants and digest them. But if the depth of snow cover and the period we have snow in the mountains decreases, inevitably we'll have more and more brown hares up here. The snow hare is an opportunistic species. It's very flexible, so it can adapt to even rapid changes. An exchange of genes with a neighboring species might also allow it to evolve more quickly and adapt to climate change. So it's hard to say whether hybridization is a good thing or not.
The arrival of the brown hare could spell the disappearance of the white one, its fluffy feet and stunning camouflage lost as snow cover disappears. It's part of a process of specific adaptations being replaced by the commonplace features of animals and plants from the valleys. Another high-altitude specialist, the ptarmigan, is also threatened with habitat loss. Like the snow hare, these birds date back to the Ice Age. Their reign in the Alps almost at an end. Today, they are an endangered species. And what about the marmots? Emerging from their burrows after 6 months of hibernation. Climate change doesn't seem to have affected the date of their awakening. They still rouse between the end of March and the beginning of April. But marmot numbers appear to be decreasing in the Alps. Females are giving birth to fewer pups. Without snow cover on top for insulation, the temperature inside the burrow drops. Researchers believe that females need more energy to fight the cold and as a result are giving birth to fewer young. The young adults may soon find themselves out of a job as they have fewer pups to keep warm and watch over. Will the lack of snow one day change the way marmot families function? The first rays of spring sunshine trigger the snow melt. Snow becomes water once more, and the cycle begins again. The beauty, the diversity, and the life snow holds safe through winter are at risk. Without snow, our world is diminished. May our actions safeguard winters. May they retain their rightful place in our calendar. and let it snow.